Okay, so what I'm going to do for you in the next few minutes is describe a summary of the research that my group has carried out during the last 6 years or so. If we want to understand climate, which often is varying on cycles longer than our lifespan, we need to look at these very complete records. And the record that we have in this region extends back at least 5,000 years, and it's at this sort of resolution, so it's unprecedented. This is one of the highest quality climate records that are available anywhere. Now, the first little core I'll show you is a freeze core. I showed you one of these ones. This was taken from Effingham Inlet, and this is where the core was taken, run from this anoxic basin in here, anoxic with no oxygen in it, so there was no oxygen down at the bottom waters right here. The bottom of the core bottomed out in an earthquake record. There was a slump in 1946. There was a major earthquake in this area, and it ended in 1993. We didn't get right up to the top because as we pulled the freeze core up, it had to come up through 200 meters of water and it washed some material away. But we went year by year by year by year by year, counting all the diatoms. We dated it, so we know all the different things that were going on around here. So we did something called time series analysis. As I mentioned, that the computers that we have scan the X-rays right here and recognize changes in the thickness of the layers and their grayscale. So the variations are found. And when we did this, we did something, I love this, wavelet analysis right here. This is a type of time series analysis which allows you to recognize trends visually in something. And so what we see here, all these little blobby bits up here is the annual layers. Every year a layer, so it can recognize that. It also recognized in here, at this level right here, that occasionally an El Nino impacts the area. The Northeast Pacific, if there's a big El Nino, has a major influence upon climate. We're a little further north. It doesn't always happen. So once in a while, we have some El Ninos. But the big thing that was happening throughout this entire record was a 10 to 12 year cycle that was dominant throughout. And we picked up the same thing when we did a different type of time series analysis called spectral analysis. We recognized an 11-year cycle in the grain size that are washed in the wintertime, and also with the diatoms. And so they had the same 11-year cycle. So this was cool. We said, what's causing this 11-year cycle? Then we went and looked at those long piston cores, the ones that were taken with these great big cores that weighed several tons that are lowered down to the ocean bottom. And this record here extends from about 2,000 years ago or 1,800 years ago back to nearly 5,000 years ago. And what we saw when we did the same sort of wavelet analysis in here was that we had all these solar cycles. The 11-year cycle is called a Schwabe cycle, but piggybacking on top of that are longer solar cycle. Here's one's called the Gleisberg cycle, which is 75 to 90 years, something called a Seuss cycle, and then a very long cycle called a Bond cycle. And these showed up here quite clearly through here. And we also, so here's the Gleisberg cycles right here, and here is the Seuss cycle, and there was a major oceanographic cut here. So I'll describe that. And here it shows it more clearly. And what I'm emphasizing here are the Gleisberg cycles, because to discuss everything would take a long time. So here's a Gleisberg cycle blipping in. This is a solar cycle which is 75 to 90 years. Here's another one. Here's another one and another one. So they gain strength, they fade out, they gain strength, they fade out. Here's the Seuss cycles. This major cut right here, 3,500 years ago, this marked a neoglaciation. There was renewed glaciation in this entire region about 3,500 years ago, which we pick up in the oceanographic record as well. So something major was going on oceanographically as well as in the ocean. The major funding for this research on the West Coast was initially from the Natural Sciences and Engineering Research Council of Canada. And the main reason I got this money was that there was problems on the West Coast. They had these major fisheries going on with various species that they go on quite nicely, then all of a sudden they crash. There'll be a major fishery one year and there'll be none the next. Problem is, their fishery records are very short. They only reach back into the early 20th century in many cases. And so the fisheries managers were very, very interested in understanding, are there cycles and trends in fishing? And so we were mandated to look at these cores to see if we could find any records of fish remains to see if they would tell something about, are there actually cycles in here? The two important commercial species we looked at were northern anchovy and also Pacific herring. Okay, and they have been found to undergo significant population changes through time in this region, and as a result they were a good target for us. Now again, because of the brief fishing records which existed for these important species, it's really important for us to go back and try and see whether they change over time, because there are huge fleets. There's thousands of people employed in these fisheries, and their success of them, they want to know, are they going to crash? What drives it? We have the same problem on the West Coast with salmon fisheries, and that they don't understand those very well as well. One year they'll have a huge population comes out of nowhere, and the next year it'll be nearly gone. They blame it on overfishing, they blame it on oceanographic changes, but no one really knows for sure. So in order to understand these things, you need to look at the longer record. Well, here's Pacific herring, and this is what we look at. This is a nice drawing of a Pacific herring. This is what a modern scale looks like, and when we look in these little sediment layers, we pick them apart, you can find fossil scales. And I have students that count these things, and they look at changes over time. Sometimes in the core there'll be almost none, other times will be very abundant, and we can employ statistical methods to try and figure out how they exist. Now, it's a cool water species, and in Effingham Inlet, it was very near its southern limit. So that's a great place to be, so if you're on the margin. And it likes conditions when annual water temperatures are above average. And so if you find warmer waters around there, you'll tend to find more of these things. So that's what controls Pacific herring. Northern anchovy, and this is a picture of its scale, and even to a person, a lay person, I think you can see there are very distinct differences in these scales, and so it's a very easy tool to try and count the relative abundance of these things. Now, it's at the northern end of its range in Effingham Inlet, and it likes it during enhanced upwelling. So lots of upwelling around, you find lots of these things. And as you saw just on that little graph, or on the X-ray of the core, that the conditions vary considerably in Effingham Inlet, and they'll vary considerably at longer scales as well. And this is what we wanted to look at. And this is what we saw, is that just as I showed you with the diatom and the sediment records a few minutes ago, the anchovy and the herring are fading in and fading out over time. And so that they have these long records. So here's the Gleisberg cycle. You can see them fading in and fading out. Here's the Seuss cycle right here. And they both underwent this major cut 3,500 years ago. And they continue to go on at the present time. Now, right now, we've finished off an anchovy regime right now. We're ready to have some herring seemingly start to come back again. But you can see enormous abundances of these things at time fading in and fading out in response to what seems to be solar cycles. So here we are at higher trophic organisms that are feeding basically well up the food chain, also responding to the same drivers which seem to be controlling the diatoms and the sediments that we saw. As we were began to develop some hypotheses as what might be controlling the patterns we were seeing, we saw all these solar cycles. What was a eureka moment for us was when we began to uncover, or we began to read literature which pointed out how climate amplifiers are influencing the solar cycle. And it's interesting, there are literally hundreds and hundreds of papers that have been carried out which have found apparent links between solar cycles and climate, which was quite heartening to us. The problem was, and here's an example right here, here's Sunspots number right here, and this looks at global mean sea surface temperature, so they match up quite nicely. Here's another record right here, for example. This shows the surface temperature over time. This is looking at changes in solar radiation, and this little dotty line right here is the actual thermometer record. They match up very closely as well. We also found solar cycles as well in other records from our region. This is one right here looking at tree ring widths in the Kola Peninsula, which is up in northern Russia, and they found the same Gleisberg cycle we see, this Hale cycle, which is a 22-year solar cycle, and our 11-year cycle. So they were very clear, and this is all across the high Arctic, and there are many, many other records as well.